Okay, thank you for the words and hello everyone. So today I would like to talk about framework for hybridization of mixed systems in MFEM. And talking about mixed systems, we have many of them, definite or indefinite, like Darcy problem in hydrodynamics, or heat conduction in thermodynamics, Maxwell problem of electromagnetics, and so on and so forth. And here are just some examples from MFEM, and also the Joule mini app, so a bit more advanced one. But the largest class, at least in applications, is probably the convection-diffusion system. Like here, we have an example of non-uniform flow of some contaminant, which is known as Kovácsny flow. And mathematically, we can formulate it, for example, like this. So two coupled equations, one for the flux Q and the other one for the potential U with some velocity field C and conductivity kappa. And in what comes, the flux we consider either continuous, discretized like with Raber-Thomas elements or Nedelec and so on, or discontinuous. But potential will be always discontinuous to benefit from properties like local conservation and so on. What's also important, we assume some symmetry of the system on the block level or antisymmetry, but that's not the same as saying that the system itself is symmetric. Actually, it's not in many cases, many important cases, like due to that conductivity or due to that convective part. But to give you some introduction, what are the challenges here? So one of them is definiteness of the problem. So the stationary problem approaches that saddle point. So this rather favors like primary formulation with single equation. On the other hand, we would like to preserve maybe divergence-free structure of the problem. So this would favor rather the mixed formulation, where basically the potential equation itself becomes the divergence constraint. And also we would like to have that conservation, that local conservation, as I have mentioned. Maybe we need to deal also with the preconditioning. We have tight coupling between the equations. It's not that easy to precondition that mixed system. Also that memory consumption or data motion. We want to avoid that memory bound computation. And in some applications, we also run into issues with anisotropy, causing some ringing and also troubles with preconditioning and so on. In summary, we would like to have the best of both, best of that primary formulation mixed, something from DGs and ideally everything together and maybe even better. So for that reason, I have developed the framework for mixed systems, which consists of these four main pillars. So on the user side, there's this Darcy operator, which helps with setup of the solvers and also constructs the sure complement preconditioner. But within the framework itself, we have primarily that Darcy form or its parallelized version par Darcy form, which constructs the block operator and eliminates the boundary conditions. And behind that, we have two backends, like Darcy reduction, eliminating fluxes or potentials, as I will get to it in a minute, or Darcy hybridization, doing that hybridization process.
But starting slowly with just classical finite elements, classical notation, the most classical formulation of all probably is a combination of Rabiart-Thomas elements with discontinuous Galerkin elements for the potential. So this the system then would look like this. Or we can take both spaces discontinuous, like with discontinuous fluxes and potentials, so that yields this local discontinuous Galerkin approach. On the right, you have the lowest order elements of these kinds. So how does that look with the classes of the framework? So that Darcy form, as I have mentioned, takes care of construction of the operators and that block operator and elimination of the essential boundary conditions. Then the true complement is constructed by the Darcy operator, which helps us also in the cases of the steady state when we are approaching that saddle point. But as it's typical for that mixed formulations, when we have some stiffness, like due to the anisotropy, we typically have to resort to direct solvers, like for example from Suits-Sparse or other. What might help us, at least in some cases, when we don't have any convection and when we don't have steady problem, we can eliminate the potential, which is discontinuous. So substituting it to the first equation. So this is automated for the user, and all you need to do is to call this enable potential reduction, which then constructs the Darcy reduction class, which I have mentioned. In any case, the code is very simple, so it might look like this. So you just construct a Darcy form, then you get the bilinear and mixed bilinear forms, and then you add some integrators like this. Optionally, you may also specify the assembly level, and then you just assemble the form. With LDG, it's a little bit more involved. So here we have those phase terms, and we need to also specify the traces, which in turn determine the stabilization of the problem. So it's some combination of the average values and the jumps over the interfaces. But specifically for LDG, that coefficient C22 is 0, which means when you look at it, in the first equation, the only term which depends on the flux is the mass term. So we can actually locally eliminate the fluxes from the system, which is again automated through that Darcy reduction. And to give you some idea, for example, centered scheme then looks like this. So what you get is very similar to classical DG diffusion. And the code is again very simple for Darcy problem. We just, compared to the previous example, we have just that extra phase term, and also here we have that stabilization term. But we might realize that actually we don't need all those degrees of freedom of the fluxes and potentials everywhere in the interiors of the finite elements. All we need for communication with neighbors are some trace values. So we may actually introduce some Lagrange multipliers, which live only on the skeleton of the mesh and weakly enforce continuity of the total flux, as described in this foundational paper. And after that, we can reduce the whole system to just global system for the traces. So this is the main content of this development branch and that associated PR. So if you would like to find out more, you may navigate there. And starting again slowly with the Raver-Thomas elements, all we need to do is basically just call enable hybridization from the Darcy form. And then this system is set up for us. And maybe I should point out that we cannot have that convection terms here because we need to restore continuity of the fluxes due to that continuity of Raver-Thomas elements. So what that means, discretely, we have some zeros here. But in the end, when we call that form linear system, we get that single equation for the Lagrange multipliers only. And after the solution procedure, we can recover that original quantities, the fluxes and potentials, through that recover FEM solution as we are used to. So the code is really simple and basically reduces down to just this single line, enable hybridization with that constraint integrator. That's it. With HDG, it's a little bit more involved. We have that traces here, but thanks to the discontinuity, we can include also that convective terms. And again, similarly to LDG, it's very much depends on the definitions of the traces. What's the stabilization? We have centered or upwinded schemes implemented for both diffusion and convection. You can choose either, you can combine them. But in the end, again, you get such system which is reduced to just that single equation for the traces. But good news, the code is nearly the same. So I just remind you, we had the HDG diffusion integrator for the stabilization term in that LDG formulation, which we use here as well, and it does the magic for us pretty much. So at the end, we again need to just call this enable hybridization. There is also a way between these two approaches with broken Raver-Thomas spaces. So the idea is we take that layout of Raver-Thomas elements, but without that continuity, normal continuity at the facets. And the advantage here is that at least locally we have compatibility of the spaces. So we don't need any stabilization term here. But due to the discontinuity, we can easily do some upwinding and solve also for convection diffusion cases. Or we can get back to that LDG kind of formulation, so that I call LBRT. So in any case, the formulation is very simple of advection-diffusion. So we just need to add these few lines for convection. So some classical conservative convection integrator and one of these two, either that upwinded or centered integrator. And here are some test cases from the paper. The slide looks a little bit different than on my laptop, but anyway, here you can see we can solve, for example, the transport of the contaminant and time evolving non-steady convection diffusion and things like that. But getting to some more advanced features, a very fresh feature is superconvergent reconstruction. So we can take that solution consisting of that diffusion flux and optionally also that convective flux if we have that convective part, and combine it with that trace variable and reconstruct the total flux, because as we know, we are enforcing continuity of the total flux here. So we can construct this continuous representation of the total flux, like on the right, and then take this total flux and use it as a source term for that original system, but with one order higher polynomials than we had originally. So then we get superconvergent diffusion fluxes and potentials nearly for free. And everything is automated pretty much for the user. So you don't need to care about construction of the finite element spaces or construction of that higher order forms. And also, yeah, at least for some typical cases, we can recognize the setup and infer the definition of the total flux and so on. We have also nonlinear convection, so then the flux is generalized, some general function. So here we use the framework of MFEM for that. So hyperbolic form integrator combined with some numerical flux, like Rusanov or component-wise upwind, or specifically for HDG, there are these two, but I'm not going into details here. But what it means in the end, the Darcy hybridization object itself becomes the system operator, and we are solving the problem on two levels: one global for the traces, and then the local within each element for that local potentials and fluxes, again with some nonlinear solver of choice, like LBFGS or Newton. So again, the setup is very simple. We just construct for example, Burger's flux, choose one of these numerical fluxes and just add it to that hyperbolic form integrator. We also support nonlinear diffusion. So that conductivity can depend on the potential. So we follow a similar pattern, and we have this new class mixed conduction NLF integrator. combined with the mixed flux function. And that constructs, in this case, some block operator. But in the end, again, you have this kind of two-level approach, global and local solver. But for the user, again, it's very simple. Here you just set up the diffusion coefficient, add it to that integrator, and that's it. And very newly, we have also support for systems of equations. So we are increasing the vector dimension, basically stacking the whole form of all these four matrices on top of each other. With that, it might help us as proxy class vector block diagonal integrator. And what we can do with it is, for example, modified example 18, so Euler equations, but now with diffusion and solved fully implicitly. And the mixed formulation already works. The reduced, that reduction supports only linear operators, so not exactly usable in this case, but in general, it also works. And currently, there's work in progress on that hybridized version. We have also multiple examples for anisotropic diffusion. I'm not going through all of them, but here you have just some illustrations, like steady diffusion with some anisotropic factor, or diffusion ring classical problem with very strong 10⁸ anisotropy along the circle. And there is also some ongoing research in reformulation of HDG specifically for such problems. Okay, so in conclusion, I have introduced the framework for mixed systems, relying on that Darcy form class, or par-Darcy form, which is that parallelized version. There is that potential or flux reduction through Darcy reduction class. But the most efficient and winning in pretty much all categories is that hybridized version of the formulation where we hybridize the total flux. It greatly reduces the size of the system, improves preconditioning, convergence rate. We have also very good stabilization, and so on and so forth. So what you can do with that is, for example, something like on the right or here. So that's a single step anisotropic diffusion convection simulation, which by many times it exceeds the CFL condition, but it's fully stable, so why not? And the solver is able to propagate the solution even this far. And newly, we have also reconstruction of the superconvergent quantities through that HDiff total flux, and nonlinear convection or diffusion. And there's work in progress on systems of equations. And there is still all the things to do. We would like to demonstrate this capability maybe in some more complex mini apps. Eventually, we would like to also get to GPU support and maybe extend the framework for Maxwell kind of problems, and so on and so forth. And with that, I thank you for your attention.
Hi, great talk. I had one question about the skeleton space. So the lambda variable, if I'm understanding correctly, and you're following the Nguyen paper, you're using L2 on the skeleton space right now, correct?
Yeah.
Have you thought about, they had a follow-up paper later on EDG, where they basically are using a sort of a continuous space on the skeleton? And you lose the reconstruction properties, but it massively reduces the potential size. I was wondering, had you considered, like, is that something you can do with this formulation? So you change that, like, MPH0 there would become a continuous space. So rather than getting duplication at the vertices, there's a single DOF.
Like the trace variable is just a single value at each edge, so you're not like duplicating anything really. I don't know if I'm getting correctly the question.
So the trace variable is always P0. So it's a single constant on the edge rather than...
No. It's arbitrary order.
So then say you had P1 at the vertices, there would be duplication because it's a DG space rather than a CG space.
Oh, you mean we have like open layout of the nodes of the polynomials, so it doesn't reuse that values at the nodes, at the vertices of. Yeah, that's true, but it naturally comes with the Rabier-Thomas elements, which are constructed this way. So I know there are some different HDG approaches, which also leverage this kind of construction, but yeah, maybe we could explore it. Yeah, I don't have any definitive answer for it right now, but yeah, we could explore it. Yeah.
Thanks.